Risk Management Lecture 4. في ال previous lecture we discussed the qualitative risk analysis فيما يخص ال probability and impact وال performance qualitative risk analysis وال risk matrix وال entering assessment into risk registers. Also we discussed the quantitative risk analysis in the area of quantifying the risk, entering quantification into risk register, reducing the risk probability curve, cost risk curve, schedule risk analysis. في this lecture we will discuss a tool with technique used for quantitative risk analysis such as sensitivity analysis, probability analysis, expected value analysis, decision tree analysis, BERT analysis, and lastly simulation. First, let's talk about the sensitivity analysis. Sensitivity analysis measures to what extent output are sensitive to the input. This means the risk. In measuring risk, we need to know what is the impact. The impact is the output. So if we change the input, how much the input, if change, will change the output, which is the project objective, such as cost, time, and quality. So that means what will be the output when the input changed. One example of sensitivity analysis is if we have a normal quantities of poured concrete in a dam project located at Aswan is 3000 cubic meters per day at an average temperature of 35 centigrade in the summer season. But the summer season temperature varies between 30 degrees and 45 degrees. The change in temperature, which is the input, could affect quantities of poured concrete, which is the output. So if we need to know exactly what happens when the temperature changes during the summer for this project, so we need to know or to link between the input and the output, and this could be done using the sensitivity analysis. This way we can use or measure the impact of the risk on the project objective. Second tool that we are gonna discuss here, the probability analysis. Calculating the probability of occurrence of one risk using probability analysis is not that easy, as it needs a lot of data. Lots of data is needed to fit the probability curve to determine the probability of the occurrence of one of the risks. These data include market data, financial data, vendors data, past experience of the project team, and site conditions, and many other data. Common types of probability distribution curve that could be used in the risk analysis for sure is the normal distribution, the beta distribution, triangular distribution, trapezoidal distribution, and rectangular distribution. Normal distribution curve, or what we can call the bell curve, is the curve shown in this graph, which could be one of the four curves here, even the green, red, blue, or magenta. Normal distribution curve characteristics include continuous random variable. That means it deals with continuous variables. Bell-shaped curve. This is one of the characteristics signifies the normal curve, which is in the shape of the bell curve. Curve extends indefinitely in both directions, even right and left. Curve never touches the horizontal axis. The mean, median, and mode of the curve are equal for the normal. Symmetric. The curve is symmetric with respect to the mean. Means the right part of the curve is symmetric with the left part of the curve. 86 of the area under the curve is within one standard deviation. 99.95 of the curve is under 2 standard deviation. 99.7 of the area of the curve under the curve is within 3 standard deviation. The total area under the curve, the normal curve, equal 1. The second distribution is beta distribution curve. Beta distribution is different from normal distribution in that it's not symmetric, as shown in the figure. Some characteristics of the beta distribution curve include it's not symmetric around the mean, probability vary homogeneously, require minimum 4 parameters to be drawn, more realistic for expressing real situation. And this specifically is applicable for risk management. Triangle distribution curve is the curve shown as the triangular. Start with optimistic point, pessimistic point, and expected point, which is the peak point, 3-point estimate. Triangle distribution curve characteristic: the peak is 1 point, which is located at the expected, the top part. Probability varies quickly around the two sides. Not necessarily symmetric as shown in the figure. Range and the peak point is quite enough to draw the curve. If we have 3 points, we can draw the triangular curve. Trapezoidal distribution curve. Characteristic is peak is the range. The range of the curve is the peak of the curve is a range between point B and point C. Data is not enough to draw other types of curve. If this happens, we can draw trapezoidal instead of drawing the beta or normal curve. Not necessarily symmetric. The last one is rectangular distribution curve. Characteristic of the rectangular distribution curve include peak is a range, and the range is AB for the peak point. Uniform distribution, that means A and B are equal. Data is not enough to draw other types of curve, beta or triangular, so we can draw rectangular instead. In general, if we have enough data, beta and triangular curve are most suitable to express probability. But in case we don't have enough data, trapezoidal, rectangular are more suitable. Can only drawn by 2 points. As a conclusion of the last two tools and techniques for quantitative risk analysis, sensitivity analysis concentrate only with risk impact, but probability analysis calculate risk probability. So it's necessary to have a tool that combines both the impact and the probability together. This technique is called expected value analysis, which is coming in the next slide. Expected value analysis, tool number 3 used in quantitative risk analysis. Expected value analysis determine the risk magnitude. Consider both probability and the impact actual values. Impact and probability are calculated using previous explained techniques, probability and probability curve and the sensitivity analysis, or from the previous experience and records of the project team. Impact and the probability are multiplied mathematically to get expected value analysis. Expected value analysis, that means expected value analysis equal probability multiplied by the impact. For example, example number 1. Consider a project with 3 expected risks. We have the first risk is changing of site condition. The second risk is delay of material delivery. The risk number 3 is late decision making. Each of the 3 risks has its own probability and impact as shown in the table. The first risk probability is 25%. The impact is 50k. Second risk probability is 60% and the impact is 100k. Late decision making probability is 30% and the impact is 25k. To calculate or estimate the expected value of each risk, we multiply the probability of the risk by the impact. So if we multiply 0.25 multiplied by 50k, we get 12,500. For the second and third, we get expected value of 60,000. For the third one, we get 7,500. So the rank of the severity of each of the 3 risks goes: the first, the most severe, is risk number 2. The second second rank goes to risk number 1, which is changing the soil condition, and rank number 3 goes to late decision making with 7,500 expected value. For the third event, let's say first we decided the expected value estimated from the previous slides as the calculated 12,500, 60,000, 7,500, and we work to estimate the corrective action or preventive action to prevent this risk from happening. And we do our calculation for the corrective action, and we end up with that the first risk, if we need to eliminate the first risk, we have to pay 40,000 for corrective action. If we decide to eliminate the second risk, we need to pay 75,000 for the corrective or preventive action. If we need to eliminate the third one, we will have to pay 3,500 to correct or prevent the action. In this case, for the third event, corrective and the preventive action should be taken. Why it should be taken? Because the corrective action is less in value than the expected value itself. So it's better to leave the risk to happen, and then it's better to take the corrective action to prevent the risk from happening. But for case 2 and for the first and the second risk, the corrective action is larger in value than the expected value. So it's better to leave the risk to happen and then pay whatever expected value from the risk. In this case, this would be a lower value than the corrective or preventive action. Example number 2. If we consider a project to have a probability of 70% to be completed on time with profit of 3 million, 15% to be completed on time with profit of 3,500,000, 20% of failing to be completed on time with loss of 1 million. What is the expected value of the profit and or loss? In this case, to estimate the expected value of profit and loss, we need to multiply the probability multiplied by the impact of each probability. That means 0.7 multiplied by 3 million, 0.15 multiplied by 3,500,000, minus 1,000 multiplied by 0.2. And this minus goes because this is the last one is loss, but the first two are profit. So the profit take plus and the loss take minus. And this end up with the overall value of the expected value of this project is 2,825,000, which is the expected value for profit or loss, and in this case it's a profit. Example number 3. If we expect to have a productivity drop that will cost additional figures in the table corresponding to each productivity. The cost of productivity drop. If the productivity drop is 25%, we will lose 110,000. If the productivity drop is 30%, we will lose 120. If the productivity drop is 40%, we will lose 150. If the productivity drop is 60%, we will lose 200,000. If the productivity drop is 70%, we will lose 250. If the productivity drop is only 10, we will gain 80,000. So in this case, to estimate the expected value of the productivity drop for all the cases, we will multiply each probability by the cost of productivity drop, and we will end up with this equation, which summarizes that the cost of additional expected cost for the productivity drop is 110,500. The next quantitative risk analysis tool is the decision tree analysis. Benefit of using decision tree is a useful tool for helping to choose between several courses of action. If we have several courses of action and we need to take decision to take only one of these courses, the decision tree will be a useful tool. It's highly effective to explore options and investigate possible outcomes of choosing those options. Form a balanced picture of the risk and reward associated with each possible course of action. So that means the decision tree will make it easy to select a decision between multiple decisions, and based on the benefits or the losses of each decision. To do this, we will have a diagram. We need to draw a diagram, and this diagram will include some drawing shapes like the decision node, the chance node, and we will calculate the net path value. To start with drawing the decision tree, first we have a decision and we draw a decision node. From this decision node we will have our decisions. In this case we have option 1 and option 2. Option 1 will lead to a chance, two chances, scenario number 1 and scenario number 2. Option number 2 will lead to a chance node with scenario number 3, scenario number 4. Each of the 4 scenarios will have its own probability and reward. For the first scenario will have the probability and reward, second scenario will have probability and reward, scenario number 3 will have probability and reward, scenario number 4 will have probability and reward. This only will make us only draw the diagram. To solve the diagram, we will multiply the probability for each scenario by the reward, and for the chance node we will calculate the expected value for the chance node by multiplying the probability and reward for first scenario plus the probability and reward of the second scenario, sum both together to get the expected monetary value. And if we minus or subtract the cost of the option, we will end up with the net path value of this decision. The same will apply for option number 2. Multiply the probability multiplied by the reward for scenario number 3 plus probability and reward for scenario number 4. This will get us to expected monetary value for the chance node minus the cost of scenario of this option. We end up with the net path value for this path. We will have to choose between the two paths based on which one is the least cost or the maximum profit. How to draw the decision tree diagram? As we explained in the previous diagram, you start a decision tree with a decision that you need to make. From this box, draw outlines toward the right for each possible solution. At the end of each line, consider the result of taking that decision. If the result is uncertain, draw a small circle. If the result is another decision to be made, draw another square. Write the decision for or factor above the square or circle. Starting from the new decision square on your diagram, draw outlines representing the options you could select. From the circle, draw lines representing possible outcomes, as seen in this figure. How to evaluate your decision tree? Start to evaluate the decision tree by assigning a cash value and the probability to each possible outcome, the probability and the reward for each scenario. At each circle, total percentage must come to 100% or 1 if fraction. Calculate the values that will help you make your decision. To calculate the value of uncertain outcomes, the circle on the diagram, multiply the value of the outcome by their probability. The total for that node of the tree is the total of these values. This means the expected monetary value. Calculating the value of the decision node, write down the cost of each option along each decision line. Subtract the cost from the outcome value that you already calculated. This will give the benefit of this decision. When you have calculated these decision benefits, choose the option that has the largest benefit and take that as the decision made. Example number 1 for decision tree diagram. If you have a project, if we need to make a decision about to build or upgrade a current planet. So the first decision or the first option for us is build a new planet, which will cost us 120 million, or upgrade the existing planet, which will cost us $50 million. if we decide to go with build a new planet, we have two chances. The first chance that the market will have strong demand with a probability of 65% to happen, and in case it happens, we will benefit or have a profit of 200 million. In the other scenario of the weak, if we have weak demand on our product, and this is a 35% probability, we will end up with a profit of 90 million. If we calculated the expected monetary value at this chance node, the equivalent monetary value of this equal 0.65 multiplied by 200 plus 0.35 multiplied by 90 equal 161.5 million. This is the expected monetary value. For the other option, we have two other chances. The first chance, if the market has a strong demand or weak demand. For the first case, 65% strong demand will lead to a 120 of profit. The weak demand, 35%, will lead to a 60 million of profit. If we calculate for the chance node the expected monetary value, we get $99 million as a profit. To calculate the net value of this branch, we subtract 120 from 161.5, and this decision would lead to 41.5 million as profit. The other branch lead to 49 million for profit. That means it's better to take this decision to upgrade the existing planet instead of building a new planet. Example number 2. We are in the way to take our decision to choose between two projects, Project A and Project B. Project A, if we decide to go with Project A, we have two chances. Chance number 1, that we profit 300k with a probability of 20%. Or chance B, we lose 40k with 80%. Making our calculation, equivalent monetary value for Project A equal 0.2 multiplied by 300k minus 0.8 multiplied by 40k. This gives us 28k. If we decide to go with Project B, we have three chances. Chance number 1, we lose 50k with a probability of 20%. Or chance number 2, we lose 20k with a probability of 10%. Or chance number 3, we profit 60k with a probability of 70%. When calculating the equivalent monetary value for Project B, we end up with 30k. Looking at both chances, both options, both decisions, it's better to take this decision which lead to more profit, 30k. Tool number 5, PERT analysis. Program evaluation and review technique is a method to analyze the involved task in completing a given project, especially the time needed to complete each task, and identifying the minimum time needed to complete the total project. It incorporates uncertainty. So this is different from the CBM method. It incorporates uncertainty by making it possible to schedule project while not knowing precisely the details and duration of all activities. PERT is used more in scheduling project where time rather than cost is the major factor. Expressing the duration of an activity as a range of, let's say, 25 to 30 days is more realistic and comprehensive than a single point estimate, which, for example, is 27 days. It is applied to very large-scale projects, one-time projects, complex projects, non-routine project infrastructures, and research and development projects. PERT depend on the estimation of 3 points. That's why we call it 3-point estimate. The first point is the optimistic duration, estimated time of executing the activity under very favorable working condition. This is the optimistic. The probability of attaining this duration is about 0.01. Pessimistic duration is the estimated time of executing the activity under very unfavorable working condition, and the probability of attaining this duration is 0.01. Most likely duration, estimated time of executing the activity that is closest to the actual duration, and the estimates lies in between the above two extremes, between 0.0 from the right, 0.0 from the left. In PERT, the given estimates of the times and likelihood of occurrence are represented as a beta curve. The formulas for the expected duration, called expected elapsed time T expected, are as follows. Expected time for activity, any activity, T expected equal T optimistic plus 4 multiplied by T most likely plus T pessimistic over 6. To calculate the standard deviation of this calculation for activity, for any activity, sigma equal T pessimistic minus T optimistic over 6. Step 1. Individual activity duration. We calculate the individual activity duration using or based on the A, which is the optimistic duration, and it is the minimum duration. M is the most frequently duration, it's most likely. B is pessimistic duration, which equal to the maximum duration. T expected activity expected duration, which equal, as we mentioned in the previous slides, A plus 4 M plus B over 6. Sigma square, it's the variance of T expected equal activity duration variance equal P minus A over 6 power 2. Step number 2, CBM calculation. Using the activity T expected duration for all activities, CBM calculation are performed following the forward and backward paths to determine the project duration T expected capital. Activity floats and also calculated and the critical activities identified. We identify the critical activities because these critical activities will help us in calculating the standard deviation of the critical path. And step number 3, distribution of project duration. Since the probability is 0.5 that each activity will finish at its T expected duration, there is a probability of 0.5 that the entire project being finished at T expected. However, the expected project duration does not follow a beta curve as did the activities comprising the project. That means the expected project duration does not follow the beta, but the activities itself follow the beta distribution curve. Assuming that the project is executed a large number of times, the resulting population of project duration may be assumed normally distributed. Step number 3, distribution of project duration. The normal distribution of project duration is defined by its mean mu and the standard deviation sigma values determined as follows for critical activities only. Sigma equal the square root of summation the variance of all the activities on the critical path. Step number 4, analysis of project completion probabilities. Using the project normal distribution, it is possible now to find the probability values associated with a specific project duration. By scaling the project distribution to the standard normal distribution, we can obtain probabilities from standard probability tables or Z tables and make conclusion as follows. Z equal desired completion date minus mu of the mean value of the expected time over the sigma for the critical activities. Some notes that the T expected plus or minus sigma equals 68.2% of the area under curve, T expected plus 2 sigma to standard deviation equal 95.4 of the area under curve, T expected plus or minus 3 standard deviation give us 99.7 of the area under curve. Variance equal power 2 of the standard deviation, and the standard deviation itself is the square root of the summation of the variance of all the critical activities. To show this in an example, consider a project whose critical path consists of 4 activities A, B, C, D. Each activity has 3 time estimates as shown here. Activity A has 3-point estimate 2, 6, and 8. B has 3-point estimate 3, 9, and 12. C has 3-point estimate of 2, 8, and 10. D has 3-point estimate of 4, 6, and 9. The first step to do is to calculate the T expected for each activity, and this is done in this table. The expected time and standard deviation is calculated for each activity. T expected of activity A equal 5.66 from the equation 4 of T most likely plus T pessimistic plus T optimistic over 6. This is done for the rest of the activities. And sigma standard deviation for each activity is calculated by subtracting T optimistic from T pessimistic over 6. And this gives us 1, 1.5, 1.33, 0.83. The expected time for the project equals the summation, because this is a very simple project that has a series of 4 consecutive activities. That means the project duration, total expected project duration, is 27.65, and the standard deviation of the total project is the square root of the variance of the critical activities as shown here. This provides us with 2.39, which is the standard deviation of critical activities only. To calculate the probability of finishing within any given time, you calculate Z, where Z equal T minus T expected over sigma standard deviation, where T is the time required, and from the normal curve we find the probability of achieving this finish time or completion time. This is the Z-score table. The BERT, second example for the BERT approach is as follows. We have an activity, we have a project that has some activities noted or called, named A, B, C, D, E, F, G, H, I. Each activity has its own predecessor to make the logic between the activities, and each activity has its optimistic duration, optimistic time, most probable time, and the pessimistic time. First thing to do is to calculate the expected time for each activity by summing the optimistic time plus the pessimistic time plus 4 multiplied by the most likely time over 6. This gives us 5, 8, 7, and so on. Standard deviation is calculated using or by subtracting optimistic time from the pessimistic time over 6. This gives us 1.31, and so on. The variance is the power 2 of the standard deviation. This is calculated in the table. First, or the second thing to do is to calculate the network. To calculate to make the calculation of the network, we need first to draw the network and put the previously estimated duration here, and solve the forward path and backward path, and identify the critical path as highlighted in the red boxes here in this equation. The overall expected time of this project is 45 days, and when we want to calculate the standard deviation of this calculation, we obtain the square root of the variance of the critical activities only. The critical activities is A, B, D, F, H, and I. Calculating all these, we get standard deviation for the whole project as 3. What is the probability of completing this project in 50 days? To estimate that, we get Z equal to the time we need to estimate the probability for, which is 50, minus the T expected for the project, which is 45, calculating from the previous slide, over sigma for the whole project, which is 3, calculated in the previous slide as well. The resultant is 1.667. To obtain the probability from the table for 1.67, we go back to the probability table. 1.67 means that we will go in this row until we meet the 0.7 coming from the top, because our number is 1.6. 1.6 is found here, and 1.7, the 0.07 is found from the top. 0.7 meets 1.6 here, so the probability is 95.25. That is the answer to this question. Tool number 6 for the quantitative risk analysis, the simulation. Using the simulation. Simulation is an analytical method meant to imitate a real-life problem or system, especially when other analyses are too mathematically complex or too difficult to reproduce, as in the case of risk analysis. Monte Carlo simulation is a form of simulation that randomly generates values for uncertain variables over and over to simulate a model. So the one we are considering here is Monte Carlo simulation. One of the softwares used in running the Monte Carlo simulation is Crystal Ball, as well as at-risk software and Primavera risk analysis. We here consider the Crystal Ball. Crystal Ball is an add-in in software for Microsoft Excel. Crystal Ball will facilitate the simulation process, the definition of the probability distribution, and the statistical analysis, but will not create the original model. In Crystal Ball, we have the capability or the option to select from the distribution gallery. This distribution gallery for the inputs include many distribution for the inputs, such as normal, triangular, Poisson, binomial, log-normal, uniform, exponential, geometric, Whipple, beta, hyper, geometric, custom, and many other. And even we have the option to fit our own probability in case we have a scattered data. Also, we can control the parameters of each probability by entering the means, the standard deviation, and whatever parameters for each distribution. One problem that we can run in the Crystal Ball with Monte Carlo simulation is one complicated problem, such as the one in this example. We have a project with many activities, A, B, C, D until B. A predecessor of each activity is shown in the table. The duration of each activity is different. Not all the activities follow the beta distribution as in the PERT example. In the PERT example, all the distribution of the individual activities follow a beta distribution based on 3-point estimate. But in this project, we have different probability for different activities. The first one, we have discrete value of 4. For activity B, we have a normal distribution. For the C, we have custom. For D, we have normal again. For E, we have triangular. For F, we have triangular again. For G, we have normal again. For H, we have uniform, triangular, uniform, custom, normal, custom, custom, and so on. We have also the cost of each activity. What we can run using the Crystal Ball, we can perform a risk analysis study and study the impact of the activity's duration on both the total project duration and the cost, considering indirect cost of 500. You can do that in an Excel sheet. We can also get the distribution of the duration and cost for the whole project and determine the probable contingency for both of them, corresponding to 50% probability, 80% probability, and 90% confidence level of probability. This ends up our presentation about the tools of quantitative risk analysis. Next lecture we will discuss the project risk management process, which is the last two processes, which is the risk response and risk monitoring. Thank you.